second part of spectroscopy I'm going to discuss about. So please, if you are new in this channel, please subscribe and like the channel and share with your friend and click the bell icon so that you can get easily notification time to time. Okay, so now start. So in last my lecture I was discuss about the IR active and IR inactive. Okay, so now I will discuss next things in this lecture. Okay, so next things I will discuss in this lecture. Next things is very important, which is basically based on whole IR staging frequency. Okay, so calculation of fundamental staging frequency. Okay, so now we will discuss calculation of fundamental staging frequency. Okay, so how to calculate staging frequency? Okay, so basically by using the Hooke's law, which permit the calculate the fundamental staging frequency, okay, of bond between two atoms. Okay, so here the basically two bonds is like vibrating as a springs, and vibration of bond is governed by the this law of physics, which is the motion of a spring. Okay, so Hooke's law. Okay, so Hooke's law is telling us about the determine the staging frequency between two atoms. Okay, two atoms, when two atoms is vibrate, and we can calculate the staging frequency between them. Okay, so this is actually the physics law, and staging frequency is equal to the 1/2 pi c under root of k upon mu. Okay, where mu is the reduced mass. Okay, this is reduced mass, this is force constant, and this is speed of light. Okay, and this is the constant. Okay, so here reduced mass is equal to m1 m2 m1 plus m2. This is the mass of two atoms. Okay, m is the vibrational frequency, which is in centimeters inverse, so unit is centimeter inverse of this stage vibrational frequency. Okay, so if we generalize this Hooke's law, so if you see CC bonds, actually I will show dependent relation. Okay, and so this 0.1, so this staging frequency is proportional to under root of force constant and inversely proportional to 1 upon this reduced mass. Okay, so what it tells about the when a force constant is increased K value is increased, then staging frequency will increase. Okay, but if the reduced mass is increase, then staging frequency will decrease. Okay, so this is reverse and this is proportional relation. So if we generalize this relation, C single bond C, so here the staging frequency will be 5 into 10 to the power 5. Sorry, this is force constant. For this force constant with this, and for C is double bond C, force constant will be the 10 into 10 to the power 5, and C triple bond C, force constant is 15 into 10 to the power 5. Okay, and similarly for CO, force constant in 1 to 10 to the power 5. Okay, so this is force constant value, and if force constant is increased, here if you see, for this case force constant is higher than other these three. Okay, so staging frequency for this will be higher. Okay, and lowest staging frequency will be for this. Okay, so this is the relation which holds for this bonds. Okay, so if you write value of staging frequency for this, so for this is staging frequency is 1200 centimeter inverse, and for this 50 centimeter inverse, and for this staging frequency is 22 centimeters inverse. So this is the staging frequency. You can see here, higher the force constant, higher the staging frequency, lower the force constant, lower the staging frequency. Okay, so this is very important. Okay, this Hooke's law. Now we will discuss about, and there are several factors which affect the this vibrational frequency, like vibration and coupling and hydrogen bonding and so on. Okay, so I'm not going in detail. So if I ask why that hydrogen bonding lower the absorption frequency, so hydrogen bonding also affect the absorption frequency, so it decrease the staging frequency. Okay, so if you increase the bond length, then obviously decrease the force constant and decrease the staging frequency. So this is the theme of hydrogen bonding. Okay, so if we see this example, here your hydrogen, this is here the negative, partial negative, and this hydrogen bond will bond with the oxygen, and here your hydrogen, this is your positive charge. So this bond will increase. Okay, when this hydrogen bond with this oxygen, because electronegativity of oxygen is higher, and okay, so this bond will move to this side, and this bond length will increase. That's why the staging frequency goes down. Okay, right. So hopefully you understood what I am trying to explain you. Okay, right. So this is the actual meaning of hydrogen bonding, how we affect the staging frequency. So now will give some data which we will get the idea of staging frequency. Okay, so it's a very general idea. So if you see similarly CH and CD and CO, so guess you which one which bond will be higher, which bond for which bond will be the higher staging frequency. So if you see you can't see from here is the only in all three spaces only the change of this atom. Okay, bond is same, so you have to decide from the reduced mass. Okay, so here the reduced mass is increasing, that's why staging frequency is decreasing. Okay, so for this staging frequency 1100 centimeters, and for this staging frequency is 2200 centimeters, and for this is around 3000 centimeters. As I told, the reduced mass increase CO rather than CS, then staging frequency will decrease. So this is general themes of how to decrease staging frequency. Similarly, aldehydes absorb higher frequency than ketone. Okay, because ketone, if you see ketone, this and aldehyde, so here for this case staging frequency higher, but for this case is lower. Because why? Because this staging frequency here two electron donating group is attaching, only one here single electron donating group is present. So if we move this bond electron from this side to this side, so here develop positive charge. So here positive charge neutralized by this methyl group, but here positive develop here positive charge, so here positive charge neutralized by the two methyl group. That's why staging frequency for this case is lower than of this aldehydes. Okay, right? And also if electronegativity is increase, if electronegativity is increase, then your staging frequency is absorption staging frequency is also increase. Frequency also will increase. Okay, so there are many bonds, lot of bonds. Ring size also affect. If ring size is decrease, then staging frequency will be increase. Okay, due to increase the S characters. There are several points. And there are some region which lie the actual staging frequency of a particular functional group. So if you see from 900 to 50 centimeters, so in this range the strong band due to CO and aldehyde, ketone and carboxylic acid, amide, ester, lactones, and for this range 200 to 3000 centimeters. In this range lie C11 CH, like aromatic, okay. And for 3600 to 3200 centimeters, in this range OS and NH2, NH, etc. These types of ligands lying this range, okay. Right, so hopefully you are following me. So, and I will give last note of this IR infrared spectroscopy. So actually the cis olefin having high staging frequency than trans olefin, okay. So cis olefin having higher staging frequency than trans olefin, staging frequency order, okay. And so this is all about finish. Hopefully I finished, and if anything is remaining you can try yourself, okay, to read your notes also, okay. So now I am going to discuss about NMR proton, NMR. So now I am going to discuss about proton NMR. This is also very important, and so basically this proton NMRs basically based on nuclear magnetic resonance. This is basically nuclear magnetic resonance spectroscopy, and this is similar to the UV visual and IR spectroscopy, okay. So here sample also absorb your electromagnetic radiation, okay, in 3 megahertz to 30,000 megahertz and okay regions. So here molecule do nuclear magnetic transition between magnetic energy level of the nuclei in the molecules, okay. So this is the basic introduction about the NMR, and so here radio frequency is 3 megahertz to 30 megahertz, okay, right. So here basically nuclear magnetic transition between nuclear magnetic transition, nuclear magnetic transition happen between magnetic energy level of nuclei in molecule. So it is basically the nuclear magnetic transition between magnetic energy levels of nuclei in the molecules, okay. So this is the basic introduction about this NMR spectroscopy, okay. So now we move to the next point. So next point is nuclear spin. I will discuss about nuclear nuclear spin is basically used in NMR spectroscopy, which is based on magnetic properties of nuclei. That is called the nuclear spin. Okay, so here just as electrons have two allowed spin states, which is designed by quantum number plus half and minus half, nuclei have. Okay, so nuclear spin quantum number I is here. Nuclear spin denoted by I. Okay, so this is right. Now inside this there are a lot of theory. If you are interested, you can go through details. Okay, I am not going in details, so I am giving roughly introduction. So if your atoms like 1,1H means odd atoms, okay, odd atomic mass, then it will be the NMR active, like this 13 carbon 6 and 15 and nitrogen 7 and 19 fluorine. Okay, so this is NMR active. And if I value does not equal to 0, okay, these are the NMR active. So point 2, if I value is 0, then NMR inactive. Those compound having spin, nuclear spin value I value is 0, then so when the mass number and atomic number is even, like if you see example 12 carbon 6, so your mass number and atomic number is same, even. That's why the this is the NMR inactive. 16 oxygen 8. So these are the NMR inactive. Okay, right. So hopefully you understood what I am trying to say. So if I is equal to half, so this is for H1 and 13B is carbon 15 and 19F. Okay, this is the exact value for these atoms. Okay, and I is equal to 1. This is for 2D deuterium 6 lithium 14, and so these are the value very important. If you are solving the problem, then these value you will use. Okay, or otherwise if any question is coming in exam, then examiner will give the this value about these values. Okay, so if I is equal to 3/2, then this is for 7 lithium and 11 boron and 35 chlorine and 79 bromine. So these are the value, nuclear spin value for different species. So now we will discuss the how to calculate the spin allowed states. Okay, so spin allowed is basically calculated by this formula. Numbers of spin states is calculated by 2i plus 1. Okay, this is the formula. So if you see examples for this 1 hydrogen atom, so I value for this is, as I told you here, half. So numbers of spin states, for this hydrogen is 2i plus 1. So I is half plus 1 is equal to 1 cancelled, 2. So spin state 2. So 2 is it will be the plus half and minus half. Okay. Similarly, we can find other species for like this 13 carbon, 15, and this is okay. Right. To discuss about some other things means which is basically based on mathematically calculation. Okay, so I will give one formula, some formula you can write as a formula. Okay, and you should remember during exam period. Okay, so formula number 1, delta is equal to gamma h 2 pi h0. This is the magnetic fields, and delta is the energy difference between alpha and beta spin states. Okay, and H0 is 10th of external magnetic field, which is the measured in Gauss, and H is Planck constant, and other thing is this is also constant. This is barometric ratio of relevant nucleus. Okay, and one more formula, if you write barometric ratio is equal to 2 pi mu hi. This is the dipole moments. Okay, and after putting this value you will get the formula. Delta is equal to gamma h 2 pi into h0, which is equal to finally mu h0 upon I. Okay, so this is total mathematical formula. So okay, and this is actually energy is like this. This is delta E, and this is minus half, this is your plus half. Okay, this is minus half, this is your plus half, and this is h0, right? So here delta is proportional to h0, right? So if we write the formula magnetic dipole moment related, so second formula is mu is proportional to I, where I is equal to I plus 1 into h upon 2 pi, and you can write mu is equal to g n mu n I plus 1, okay, into h upon 2 pi. So this is also important formula, okay. And third is equal to minus mu h0 this. And last one formula I will give, fourth, which is very important. Delta is equal to Gn mu n h0. So this is Bohr-Einstein relations, and if you put here h nu, look on this, and mu you will get Gn mu n h0 upon h, okay. So this is very important. There are a lot of questions have been asked in exam, okay. So now next thing I will discuss about the chemical shift, okay. So this up to here, this the mathematical. Now I will discuss chemical shift, and okay. So this is also very important. Because J coupling constant and chemical shift, all those, if you have given any complex, then examiner will ask what is the chemical shift and how chemical shift will affect by adding different functional groups, okay. So different roles having different in functional groups, and how affect J coupling also, okay. So now we'll discuss chemical shift. So what is chemical shift? Chemical shift is basically which is terms in hertz by setting of TMS peak. TMS peak is tetramethylsilane peak at 0 hertz, okay. And this magnetic fields decrease towards left when the chemical fixed are given hertz by applied frequency must be specified in megahertz, okay. So this chemical shift is directly proportional to strength of applied fields, okay. So chemical shift. So what is chemical shift? So this is directly proportional to the strength of applied field at 0, okay. Strength of applied field at 0, and this chemical shift value is equal to the difference of sample minus difference of reference TMS, tetramethylsilane. This is the actual chemical shift is in ppm, okay. So if you write the formula chemical shift ppm, which is equal to chemical shift hertz divided by instrument frequency or oscillating frequency in megahertz into 10 to the power 6, okay. So this is the formula. So if you note, increase the electron density then increase will be the shielding effect. Okay, okay, and also increase the fields which you are applied. Okay, so there are some particular chemical shift for particular species. So for methyl, chemical shift is standard chemical shift is delta value is 0.9. okay, similarly for this CS2, chemical shift is delta value is 1.3. similarly for this C, chemical shift is 1.7. okay, so here basically we can write other points. Shielding increase with increase the applied field and inversely proportional to the delta value chemical shift. If any species having higher shielding, then chemical shift will be lower. Okay, and similarly if we write the chemical shift of this benzene, so benzene having chemical shift is 7.50. okay, so these are the standard value of chemical shift directly you can use. So now I move to the other species, like important species. I'm not giving all species, but some selected species I will give chemical shift value. Okay, so like one is benzene, okay, 7.27 something like that, and other things I will tell you. Vinyl like double bond H, delta value is 4.7 to 6.5. okay, and next is allylic, chemical shift value is 1.5 to 2.0. Similarly, if any releasing group is present in your benzene here, okay, so electron releasing group means your ortho or meta position will be what? Electron rich. So if electron rich are shielding, then your delta value will decrease. Okay, delta value is decrease. If we see any examples, if you take this, if you have a methyl group, so methyl is an electron releasing group, so here your chemical shift value for this ortho position is become 7.03. okay, so chemical shift will increase the shielding at ortho and para position. okay, if any electron withdrawing is attaching, then chemical shift value is increase. okay, at this position, so it become 8.48. so chemical value is just increase. So as I told, the relation increase shielding, chemical shift value will decrease. okay, so I will give some general in actually in aromatic species like 18 aniline. The chemical shift value for inner hydrogen is high. Delta value for inner hydrogen and lower for outer hydrogen. Means less shielding. Okay, for anti-aromatic it become just opposite means the delta value become lower in means high. Here is high for inner hydrogen and lower for outer hydrogen, but here become lower for inner hydrogen, become high for outer hydrogen. Okay, delta value, right? Next thing I will discuss, which is also very important. So next thing is coupling constant. This is the last things of this NMRs. So coupling constant. Which is denoted by J. Okay, so here you denote the in hertz. Okay, so J value is denoted in hertz, RCPS, and never in delta, and never in ppm. Okay, so always unit in hertz. Okay, unit in hertz. So if here if you write 0.1 for geminal coupling when a proton attached to same carbon like this, HP, HA, and here are like difference. So JAB value, coupling constant value 10 to 16 Hz. Okay, for this. And similarly for this J value become just low, 0.3 Hz. Okay, and similarly second, if you see vicinal coupling, so for vicinal coupling, when a proton attached to the adjacent atom, okay, proton attached to the adjacent atom, if you see this. So here one proton P, here 1 proton A. So for this coupling constant will be 6 to 8 Hz. Okay, and similarly this value also you have to remember. Okay, so next things which is very important, third for trans J coupling, trans J coupling is higher than that of cis. So trans J trans coupling constant will be higher than J cis, higher than J geminal coupling. So for trans the value is HP HA, the value is JAB is equal to almost 12 to 18 Hz, and for cis this value is become 6 to 12. Okay, so for trans this value will be higher J value coupling constant, for cis it will be low, and most low for this gem. Now fourth, long range coupling. So for this long range coupling, when a coupling between protons separated by more than 3 bonds maybe occurs in olefin, acetylene, aromatic, heteroaromatic and stringing systems. Okay, so long range coupling when 2 protons separated by more than 3 bonds. Okay, if you see this, see this HB and your HA, so separated by more than 3, so 1 2 3, okay, 4, so separated by 4 atoms. So this is the long range coupling. Okay, and allylic coupling, they also when a conjugated polyacetylene chains coupling maybe occurs through the manage. Okay, so these are the data you have to keep in your mind during solving the problem. So these are the very important. So I think I covered all things. Okay, so maybe anything if I missed, so please you cover, and also you inform me, I will take further. Okay, so thank you, bye bye. Okay, good night.